The Gram-Schmidt algorithm. So our last lecture was on QR factorizations, and hopefully I was able to convince you that if we have A equals Q times R, our lives are a lot easier when it comes to solving things like projection problems and least squares problems. But one thing that was notably absent from that lesson was, well, where do we get the QR factorizations from? And one answer to that question is an algorithm called the Gram-Schmidt algorithm. Before we dive into the algorithm, however, I'd like to just maybe present some geometric motivation that sort of like props up the idea of the algorithm. So let's start with a geometric question. Remember, in QR factorizations, the columns of Q are orthonormal. And an orthonormal list of vectors is a mutually orthogonal list of unit vectors. So let's say we're in a situation where we have a basis, v1, v2, of a vector space V. So for the sake of conversation here, we're assuming that V has dimension 2. The question we're asking is, can this basis be converted to an orthonormal basis, Q1, Q2? So if you have a basis, maybe that basis is not orthonormal. So is it possible to convert that basis to an orthonormal basis of the same space? So let's look at this situation geometrically. Maybe you have your basis vectors v1 and v2. And I've tried to depict these vectors in this image in such a way that it's clear that they have different lengths, which means that they're not both unit vectors. And they certainly do not form a right angle. So these are not orthogonal to one another. So how can I get from this figure to a new list of vectors that is orthonormal? So this idea is going to manifest itself in two stages. So the first thing I'm going to do is I'm going to define a vector called W1, and W1 will equal V1. The next thing we're going to do is we're going to define a vector W2 by looking at how the vector V2 projects on to the vector V1, which is W1. So if we look at our figure here, the idea is that if I look at the projection of V2 onto V1, that defines this vector W2 that forms a right angle with the vector W1, which is equal to V1. And if I look mathematically what's going on here, I can look at the figure and figure out how to get from start to finish for W2. I go against the projection and then with V2. So W2 here would equal V2, this second vector in my original basis, minus the projection of that second vector onto my first W1. And remember that the way that we think about vectors geometrically is they don't have an inherent location. So I've drawn my vector W2 here because it was useful to think in these terms. But now I'm going to just rewrite that vector at the place in such a way that it starts where the original W1 starts. And so now the idea is that I've used linear combinations of V1 and V2 in this clever way that that allows me to redefine define new vectors W1 and W2 that are orthogonal to one another. But here's the thing is, I don't want just an orthogonal list of vectors. I want an orthogonal list of unit vectors. So how can I make W1 and W2 unit vectors now? Well, this is the idea of normalization. I can define a vector Q1 as the normalization of W1. So I take W1 and divide by its length. Then I can define another vector Q2 by normalizing W2. This is W2 divided by its length. So if you think about the process we went through here, this is sort of the idea behind what's called the Gram-Schmidt algorithm. The Gram-Schmidt algorithm takes as an input any basis of a vector space. In this example, I used a basis with two vectors to geometrically illustrate my point. And the first thing it does is it produces one new basis, W1, W2. And W1, W2 is a mutually orthogonal basis of our space. The problem with W1 and W2, however, is it's mutually orthogonal. W1 and W2 are mutually orthogonal, which is great, but they're not necessarily unit vectors. So when we normalize each of the w's, we get this basis q1, q2, and q1, q2 is orthonormal. So this is the idea behind the Gram-Schmidt algorithm. And so what we'll do here in a moment is I want to explain this proj notation, because we use this proj notation in the description of the algorithm. Then we'll describe the algorithm, and then we'll see how the algorithm helps us calculate A equals QR.